And sorry for the delay. My name is Constantin. Apparently, I cannot do Google Present. And my talk is about clustering in computer vision, from theory to applications. Clustering is something all of us have maybe seen in your bachelor's or master's, or maybe just applied k-means sometimes. So it's a relatively common concept that everyone has some feeling about, but most of the time in computer vision, it falls behind these fancy new models where you see like the 3D segmentation models or YOLO or similar things. And in this talk, I just want to present some basic ideas about clustering, potential shortcomings, and how you can apply these methods to general computer vision tasks. So, what is clustering in general? So, clustering basically tries to group data points together based on some principle of similarity. The similarity can, for example, be shape, texture, objects, or any semantic meaning that you might have. And by this similarity, you group these based on how close they are on the metric that you choose. This idea was first designed by like Gestalt psychologists, which have defined this in the beginning of the 20th century as well as the end of the 19th century, like what are concepts that the human mind perceives to group data together or group points together. And this is basically a key to visual perception. Elements in a group can have some properties that result from some form of relationship. In the example image on the right, you have the basic ideas of Gestalt clusters, where many people have looked at and considered the group based on the color groupings, the different points to belong to a certain same identity. And this is also similar to the general human perception, which is targeted towards simplicity. When we are, however, now in this new age of deep learning and big models, we focus more on, on how can we learn proper representations, how can we get our models to get groupings that we either assigned prior, like due to ImageNet classes, and train a network on these classes and automatically perform these groupings that we might want. However, also in recent days, there have been more trend towards unsupervised representation learning, where you don't want to focus on certain classes, but still want to group your data together based on like features that lead to images of similar categories to belong to the same cluster. However, when applying these representation learning approaches, you might group this data together. However, the proper assignments of which data points belong together is typically unknown. And here the clustering problem basically comes in, where we try to distinguish between disparate clusters where the number of clusters is not known a priori. And in this talk, we basically go over 4 concepts of clustering methods and just show what they can do and what potential downfalls they might have. We begin with partition-based clustering, which is basically the clustering category that most of us might have already worked with. Here you define clusters as a fixed sized partition, and you basically try to minimize intercluster distances with like an expectation maximization algorithm or maximize likelihoods in model-based approaches. And typical methods here are k-means or Gaussian mixture models. And for example, if you have really good embeddings fitting to your tasks, for example, in this image on the right, in these supervised embeddings of the ImageNet dataset, you get really trivial groupings from your k-means clustering. Well, in this case, k-means plus plus, which has a bit better initialization. But in the end, you get basically the classes that are intended. When we now, however, transfer to like a more realistic case where we don't have the embedding known prior and use some unsupervised embedding like DynoV2, the visualization looks like this, a bit more complex. But well, if your data is well rather easy, k-means can already predict similar clusters as in your ground truth data. Then we now move to Gaussian mixture models, which is a similar approach to k-means, also using expectation maximization with Lloyd's algorithm. We try to basically fit these data points onto a mixture of Gaussians to better define the shape of the individual clusters. And this is also visualized on the same DynoV2 embeddings, which have now a bit of a more dynamic shape of the individual clusters, which might have some positives and some negatives, but in the end, it's a bit more fluid than when compared to k-means. But the question now is, when we have these partition-based methods, what can go wrong, right? And a big problem which plagues many of these clustering algorithms that we go over today is that they ignore geometry. Like many partition models assume a specific shape of the cluster, like hyperspheres or ellipsoids in 2D, and the topology of the data is typically ignored. So when we look at this really simple example of the moons or rings data sets, we can see that k-means typically moves in the optimization steps towards these ellipsoid type approaches, which might not capture your data as it should be. Another problem is in data sets which contain a lot of transforms, like the COIL20 dataset, where there's basically different SO2 transforms applied to 20 sample images. This might also lead to problems when now applying clustering. So, for example, here we can see that k-means typically ignores these ring-type shapes in the latent space of the individual samples, and might even cut up or assign multiple clusters to the same object, even though, well, they might just be different in terms of rotation or similar. You might ask, COIL is a really trivial data set. Where does this apply? This applies for many different tasks. For example, on the top, we see novel view synthesis, which Dan mentioned earlier, for generating different views in your car driving scenarios. You might encounter this in reinforcement learning settings, where you might have similar types of views on the same setting for a certain task, or you might have this in like 3D construction type data sets like HorizonNet. A different problem is the cluster assignment. So, for example, if you have an unfortunate initialization, it might lead to clusters that should be glued together being split apart. And for this, the right initialization is the key, right? K-means plus plus offers a bit better initialization and is basically the go-to way for initialization in libraries such as sklearn. But a different approach, which you might not have heard about, is that you can also start with a larger K, right? And then perform something called a Dirichlet process Gaussian mixture model to iteratively remove Ks if they do not fit certain criteria to come to the proper amount of classes or clusters in this sense. However, these fixes can be slow. For example, k-means obviously needs multiple iterations to converge, but this is rather fast. But like these more complex settings like Gaussian mixture models or the Dirichlet process might lead to significant improvements in time. While dimensionality reduction like PCA or t-SNE can improve the clustering process, they themselves deliver also certain types of issues. For example, t-SNE, if your data set is large, can also take a really long amount of time. Or PCA loses information that you might need. Yeah, but let's move towards hierarchy-based clustering. So hierarchy-based clustering is often split or basically split into two different variants. One is top-down, where you basically assume you start with one cluster and then divide it up by potential partitioning criteria, like in graph partitioning. And bottom-up approaches where you start basically with each sample as individual cluster, and then you merge these clusters based on certain criteria. In this talk, we will focus more on the second one because many of the approaches that are commonly used will rely on this concept. So basically, you have these, you end up with these types of dendrograms where, well, you build up on your splitting or merging criteria, how you can individually merge or split these individual clusters. And there you have these algorithms like hierarchical agglomerative clustering, where you start from a single point and then merge in each step based on a linkage criteria. This can be really simple, like what is the nearest neighbor of your cluster in your current step? What is the furthest away, or what is the max distance between the different clusters of the individual points of the clusters? Or you can just look at the average between the individual cluster, the average distance between the individual clusters. An often used criteria is the Ward criteria, which combines different aspects to deliver a bit more reliable clusters, but also has a bit of a downside in terms of compute. Generally, HAG is a rather slow clustering algorithm, which if your data sets go towards like millions or billions of sample points, it is potentially suboptimal. But now let's go to what can go wrong with HAG. Also, similar, like this will be for every clustering algorithm. We have problems with geometry. And this can basically happen at different, more commonly at the higher levels of the tree, because on the bottom, you basically start with individual points. But if you use, for example, Ward criteria, the method is really similar to partition-based methods and thus behaves also similarly in terms of how they link together. And you might also have the problem of where do you cut your tree to, well, stop, right? Finding the right number of clusters is really problematic in these types of approaches. Because, well, it takes a long time to compute, and where do you stop? But let's also go a bit on to density-based clustering methods. One of the most popular algorithms there is DBSCAN, which basically assumes a certain density parameter around your points. So you basically form a radius and merge points together based on if they lie on this, well, epsilon, as well as the minimum number of points. Here, you also can have a few downsides. For example, here, when we choose the radius too large, we might merge clusters that should not be merged, right? And thus get like super clusters. Another thing is if you choose your radius too small, while this might work for a lot of cases, you get your proper separations of these, for example, rings. If you now have, at some points in your data set, distances that are larger than your certain epsilon, you do not connect clusters and thus will not be able to capture your data in its entirety. Let's go a bit about hybrid methods. One of the methods that tries to solve these issues that DBSCAN has is HDBSCAN, which basically tries to compute relative relative densities by looking at the nearest neighbor graphs of the, or not nearest neighbor graphs, but like the nearest neighbor distances, usually up to the fifth nearest neighbor, to define how points might be grouped together. And then they basically build a tree similar to the single linkage system in the hack algorithm to then merge the individual clusters together. If certain clusters have too little amounts of points, they will not be included in the tree, and thus the algorithm becomes a bit more, well, stable in comparison to DBSCAN. Another hybrid algorithm is the FINCH clustering algorithm, which basically just works on the nearest neighbor graph itself, and it does not look at distances at all. So basically, for a given data set, you compute your nearest neighbor graph, which basically is a really sparse matrix, which only contains for each sample point its nearest neighbor. And then you try to find different types of groups which point to each other. You form the, and then afterwards, you merge these groups to one cluster. And this is something you can then repeat for multiple hierarchy levels because you merge these different groups, compute the mean, and repeat the process. This is a bit of a hierarchical as well as a partition-based algorithm. And well, if you look at this, you can start from your standard data set, you find your first initial groupings, and then go on, find the mean, merge again, and until you basically have the final data set clustered in its entirety. This is a really fast algorithm, which also scales well, but has the issue that let's go over the issues. What can go wrong? Also, we ignore geometry. So, for example, if we have the same issue that partition-based algorithms have, which becomes more extreme in higher levels of the tree. Because, well, we now merge, you can imagine it like merging these types of ellipsoids together. And if your data set does not fit towards ellipsoid or hypersphere samples, you will merge samples together that should not be merged. You can obviously apply some geometry-friendly algorithm to better adapt the merges to your data, but this is like a bit of a hands-on approach and adaptation to the algorithm. And for HDBSCAN, for example, you can have differences in the densities on the manifold, which are not captured by these fifth nearest neighbor distances to define your densities, because it is more focused on the ambient space. If you have like sparse clusters, you might merge them, even though in a visualization, you can imagine that they should not be merged. Similarly to many of these methods, you can apply dimensionality reduction methods to get a more manifold aware type of solution, but also comes with downsides. Another point that one should maybe consider when applying clustering algorithms is the evaluation and the number of clusters. How do you choose them? In terms of evaluation, there are two types of concepts that one has to keep in mind. One is the internal metrics, which basically measure how clean or some type of quality without external knowledge, like in intra-cluster and inter-cluster distances, how do they match up against each other? And typical metrics that result in this are the silhouette score and the Davies-Bouldin index, whereas you can also do more like interpretable analysis with external metrics, assuming you have a ground truth data set, like for example, if you cluster ImageNet, where you can compare your cluster metrics against the ground truth in terms of the adjusted rand index or normalized mutual information. This is also somewhat suboptimal in the sense if your data has multiple potential possible class or class assignments. There you might, if you use an unsupervised embedding, like DynoV2, you might get clusters that are reasonable, make sense, but in terms of actual score, you get bad numbers. And then it's really hard to interpret what is the source of your, in quotation marks, bad solution. The next point is also estimating the number of clusters. This is also subjective, depends a lot on the data. And while there exist methods like the elbow method or gap statistic, or like in the Dirichlet process, methods to discard certain clusters, it is in generally, let's say, an open problem and relies a lot on like playing around, finding the right hyperparameters, and let's say eye tests, because they might not work out of the box. Hierarchy-based methods hereby can help, like HDBSCAN or FINCH, because they provide some assumption, in the results some assumption they make about the data. Also, one thing to keep in mind with these different clustering algorithms is also the runtime, which is like really applicable to like real world. So even for like 10,000 samples, a method like HDBSCAN takes a minute, whereas the standard k-means takes less than a second, or like with better initialization takes 2 seconds. And like when you now go towards standard sizes for computer vision, like ImageNet Plus, or when you consider like the Dino3 pre-trained dataset, which has like 1.7 billion images, when you want to cluster these, you might rely more on the k-means type of clustering algorithms because they are scalable, whereas HDBSCAN would probably never finish or even fit into memory. And this is also something one has to consider in terms of runtime is the number of clusters that you choose, for example, with k-means. So while k-means scales rather okay, if you increase the number of clusters, the runtime also increases. And while the DBSCAN works rather fast on small clusters, well, once you move towards like the million or billion scale data sets, you will probably never finish seeing at the end of the method or fit it into memory. Same problem, right? Whereas like you can do something like FINCH. I like FINCH because it's really sparse, takes less memory, and is also fast. The problem hereby is always finding the proper level of hierarchy. But this is a problem that is similar to k-means, like finding the right number of clusters. But let's look at some computer vision use cases, right? One example to which clustering can be applied is multimodal retrieval. Assume you have a series like Planet Earth, where each of these episodes takes an hour, and you want to find a certain clip of something. Sure, you can now apply your vision language model for videos onto 8-second clips for the entire data set. But this is like really cost inefficient. Because, and basically you want to find the right way to split the clips, right? You don't want to have, for example, a snow leopard and an ice bear in the same clip because you want to find only the snow leopard. So what is one way to how we can approach this? So we can start, for example, with a standard video, extract the frames. Like this is a really simple pipeline, right? Use a vision language encoder like Ziglib v2 or Dynotext or anything you can think of, standard clip, and get frame level embeddings. Then you can apply a simple clustering algorithm like FINCH, where you, in addition to the standard clustering target of like similarity, you also take into account the frame-wise distances, like how far they are apart. And from this, you can basically extract different video segments, which are connected to each other of similar like semantics. And then you can perform this problem for the finding the right clips as a simple retrieval task, where you now say, where's the proper like video of a snow leopard, and it gives you, or like gives you these clips, and you can now say, give me footage of snow leopards, and given the clips, it will return these top 5 retrievals. Yeah. But this is like one use case to which you can apply clustering. Another is like general data understanding and curation. Let's start with a standard problem which many of you have potentially looked at when you find a new data set, get some embedding, and start to visualize it. And for this, many people use PCA, t-SNE, UMAP, but there's also a way to directly visualize the clusters that you have in your data set if you use something like HNNE. Why might you want to do this? Well, sometimes the clusters might be reasonable in methods like t-SNE, like in the way they find themselves on the manifold, but it's hard to pick them out if you don't know the ground truth. And something that shows you the clusters on a visualization standpoint can be helpful. What does HNNE do? It basically uses the FINCH hierarchy, starts with a preliminary projection using PCA, and then moves points together if they belong to the same cluster. Basically, they enforce the cluster hierarchy in every step to basically get the different points if they belong to the same cluster, like in different sub-areas of the cluster of the higher hierarchy. And then you can try to use this for visualization and annotation purposes. You can now visualize the different clusters and mark them with like with like brushes and so on to assign them to certain clusters. You can interactively go through your data in like multiple dimensions, however you want to use them, and then have achieved much faster annotation times for your large-scale data sets. We did a user study one time which basically compared like standard annotation practices with like this latent space annotation, which basically showed a significant speed up for multiple types of data sets. Sure, if your source embedding is faulty, this will also lead to loss in annotation performance. But these can be filtered out through different post-processing steps as well, and give some initial insights on which you can start building your projects. Now that we've looked at a few examples and so on, let's come to the end and what we should take away from this talk. There are a lot of trade-offs between these methods, and they all have their own like niche to which you should apply in which you should apply them. And the major concern is obviously accuracy versus speed, and that depends a lot on your data set size. So, for example, if you use like small network analysis or like text or time series, you might have hundreds, thousands of samples. You can use something like HDBSCAN and will probably return your best results. But if you now have billions of data points, well, might make sense to take a look into more scalable approaches, maybe use hierarchies of these, or apply them in different settings, or like in sequence. Also, many methods and these implementations of these methods have issues with not only computational time, but also memory usage. while something like k-means will probably always run, will obviously always fit into memory and run fast, something like HDBSCAN will have issues fitting your billion scale data set. And also, one should consider the importance of the distance metrics. This always depends on the base representation that you have. Sometimes cosine similarity makes sense, sometimes Euclidean, and no matter what, it changes the effect on your groupings. And this also obviously also depends on the modality, if you have tabular datasets, for example. And you might have to think of what metrics make sense to use, because not every metric is fitting for every purpose. This is something that many fields plague, but it's not different here. This is basically my talk. I hope I'm in time. I have no clue. Presenter view does not work. I'm really sorry for the beginning. And I might have missed some points that I wanted to say, but oh well.
That's okay. We appreciate it. It was actually very good. Good overview and good in-depth examples. We did have one question, but you actually answered it in the last 25% of your presentation. People were looking for practical applications or examples of clustering, and you actually ran through all of those. So
I think
go ahead.
Just on this point, like I think the most prominent example for these clustering algorithms has been now in the Dino models, right, of Meta, where they have applied clustering on like their large billion scale data sets to filter ineffective samples or like curate the data set in a way that enables self-supervised models to perform better. And this is something that they use the hierarchical k-means. This is completely fine. And works well for them. It scales really well. But if for your data set, like audience, right, your data set, if you might not have these internet type data, maybe a different clustering algorithm might also fit for you. So the entire clustering field for me feels a bit of playing around and finding out what works for you. But yeah, sorry on that point.